All right, everyone. Let's go ahead and get started. I hope everybody had a good lunch. We're going to, again, kind of continue with the theme of a little bit of a informal lecture, kind of a hopefully gentle start to the week. So we're going to be talking about data wrangling, which is actually a technical term. A wrangler is, according to Webster's dictionary, short for horse wrangler, probably a partial translation of the Mexican Spanish. Somebody want to pronounce this who speaks Spanish so I don't embarrass myself? Awesome. Which is a ranch hand who takes care of the saddle horses broadly, or in other words, a cowboy. So how, as astronomers, are we all like cowhands? Well, data are often like horses in that they all differ, they rarely conform to a single standard set of behavior, and most importantly, they both love to eat hay. Thus, in our efforts to better understand the universe, we must often manipulate, coax, and in some cases force our data to behave. So this involves a large variety of tasks, such as gathering, cleaning, matching, restructuring, transforming, filtering, combining, merging, verifying, and fixing data. And I'll come back to this point in a moment, but in reality, most data sets aren't like the data sets that we work with in the DSFP, right? So when we're doing a lesson on machine learning, we want to learn machine learning. And so somebody, probably Adam or I or a guest instructor, has gone through and gotten some data set from somewhere and spent a lot of time getting rid of the hard parts of working with that data so that we can focus on the thing that we're learning that is going to be much more, maybe conceptually more abstract. And so that person has gone through these steps. They've gathered some data from somewhere. They have looked for errors in the catalogs. They've matched columns. Maybe they've restructured it so it's a little easier to understand how things are related. Or they may have gone through and done some of these other steps, right? Combined multiple catalogs together from multiple places. The reason they have to do this is, or the reason that anybody has to do this, is that there isn't a single person in the entire world that would organize the data exactly the same way that you would, right? So every data set out there, even ones that are highly polished, are not quite going to be in the format that you would prefer for doing your science with. So you may find that some data that's useful is not organized in an optimal fashion, and so the first thing you're going to do is you're going to wrangle the data. One nice thing about being an astronomer is that at the very least, all of the data that we work with, for the most part, are numbers or some other kind of nicely structured data. I guess images would be the kind of other thing that as astronomers we often work with. But an image is just a set of numbers on a grid, right? So most astronomical data can be organized into a tabular structure, so we're not dealing with oftentimes really unstructured data. It's kind of an open research question in astronomy about how you deal with very highly unstructured data. But even with a simple set of numbers that can be organized into a table, you're going to still run into problems where you're going to have to spend a lot of time just cleaning and massaging the data into a format you can use. So as an example, consider the following street names for Adam's best friends from childhood. Do you notice anything interesting about this list of street names? And I'll maybe give everybody 30 seconds. Raise your hand when you notice what's interesting about this list. Okay? I'm going to give people just one more minute, but okay, I'm seeing a fair number of hands. Would somebody like to volunteer to point out what's interesting about this? Go ahead. Okay, so there are repeats. Is there something else that's interesting? I saw Kirsten's hand first. Yeah, okay, so do we think it's likely that there are two streets in Adam's hometown, one that's spelled Reese, R-E-E-S-E, and one that is R-E-E-C-E? Probably not, right? What do we do? So For this data set, it's a small data set confined to a geographic area, so we can go look up the street names in Adam's hometown and see if there are two streets with those slight spelling differences. And we can also check and make sure that maybe there are duplicates going to the fact that some of these are duplicated. So then we can manually intervene with a correction. The problem is, even though this could catch some errors, right, where Reese and Reese are one is an incorrect spelling of the same street, it wouldn't catch an error where, for example, somebody just entered Reese when they met something that wasn't in the data, right? So we wouldn't be able to verify the data set even if we had access to all of the original street names. As a side note, Adam grew up in Evanston, Illinois, and I don't think any of these are actually street names in Evanston, so I think Adam was lying when he gave me this list. So perhaps another verification issue. The point here is that you really need to have a historical record of the data and its origins in order to do these kinds of verifications. And so this is the process of producing databases that have this kind of historical provenance is called logging, right? And so what we're really talking about in discussing data wrangling is the same thing that we were talking about this morning, which is the importance when you're doing a large project of having a clear record of what was done, how it was done, and why it was done. So a really nice paper that goes through this is this data wrangler paper, which introduces this tool. So this tool automates doing a lot of these things. So we're not going to have you use it today. I looked up, there are some interesting Python equivalents. But regardless of whether you use a really nice tool that will handle a lot of this for you, you should make sure as you're working with data in your research that you are keeping track of the transformations that you apply to that data, logging those transformations, and make that log available to anybody else who might be using your data as well. So this Wrangler tool, which is a classic, automates doing this, which is really nice. And as I sort of just said, we should be doing a better job of this in astronomy. It doesn't seem to me to be a standard convention that people really follow to provide logs of data transformations that they've applied, but that is something that you should definitely do with any data sets that you publish. As I mentioned, most of the time that you actually spend working with data is going to be spent on these data manipulation and quality checking. It's not going to be spent on the fancy machine learning things. And I think as anybody who has done a data-intensive project will tell you, if you don't spend the time up front to really investigate your data and worry about the data, you are going to run into problems later in the project when things don't work as you think they have, or when you find an error and things are broken. You're going to have to spend this time at some point. So today we're going to work through several examples that require you to do this, and hopefully you'll gain some intuition and strategies that will help you to minimize the amount of time that you spend on this while still doing it robustly. So that's all I had to say to sort of introduce the exercise. So the exercise is in the GitHub, which you should have cloned from this morning. So you shouldn't need to do anything else to get the new exercise. It's called Corralling Unruly Data. This is an abridged version of Adam's earlier version. So I've taken a couple of things. So the first part will walk you through how data is written and when writing and saving files can cause changes in the data. And then the second part will walk you through a really gnarly example of data wrangling from one of Adam's papers. And after you work through that, you're going to have to work through this for real. So you're going to be given a very poorly formatted data file and have to sort of figure out how to edit and read in that file in a way that allows you to interface with it using the tools you have available to you. If you get through that, the last problem will walk you through the Titanic data set, where you will do some basic machine learning things to predict survivorship rates for the Titanic. So that's the rough overview. As people start to get through problem 2, I will interrupt and we'll walk through problem 2. So in the problem version, I've provided you the solution to problem 2, since you will need that in order to have a chance at solving problem 3. Yeah, okay, that's all I had to say to introduce this. So I will be around to help out, and we will have a break at 3. So, yeah. I think there's wise data in problem 3 also. Plenty of wise data to go around. OK, so hold on. So if you take a look at the data file that was provided, yes, it's very small. Better? OK. So if you take a look at the data file that was provided, this thing has a really horrific format. So we're going to have to wrangle this data into a format that we can deal with. And so the fun part here is that, as Adam notes in the setup for this problem, this is a standard machine-readable, nice file format that's provided by people who know what they're doing, right? And so even with all of that being said, you still have a file format that's very difficult to work with. So Adam provides a couple of possible solutions to dealing with this. And I wanted to sort of walk you through, at least conceptually, what's going on here. You can use this as a model for the solution to part 3, which will have you work through this on an even more poorly formatted table. So what Adam does is he says, OK, we're going to open this poorly formatted file. Let me see if I can make this bigger. I might not be able to. OK, awesome. So I can. So we're going to open this poorly formatted file, and we're going to read in all of the individual lines. And then we're going to loop over the lines, and we're going to look for the first time we hit this symbol. So if we go back to the text edit here, we're looking for this row, which has all of the names for the different columns in it. So we're going to look for that, and we're going to look for the first one. And what I was just talking to Scotty about is we're going to ignore these other ones. So we're just looking for the first one that has our sort of header information in it. So we can go back here, and that's what this line does, is it says as soon as I find this symbol, I want to go ahead and replace it with commas to make this into a nice comma-separated, comma-delineated file. And it looks like we're also going to replace some extra spaces with, we're going to replace the spacing as well. So then we're just going to take the first set of these. So we're going to lop off a couple of extra things that are in the header that we don't want. And we're going to, as we do that, we're going to split on the comma. Then we're going to go back and we're going to read through the file, and we're going to skip the line numbers corresponding to some of the extra junk that's in there. And the result of doing this is to give us this somewhat more nicely formatted table. So that was kind of the logic, right? So the exact details here, you should go through and look at the text file, make sure you understand. But the exact details aren't the important part. It's the sort of logic of going through and replacing things so that it becomes nicely formatted. Yeah, Marcus?
Just a curiosity thing.
Yeah.
Is it redundant to have the list call there since it gives you a list?
Possibly, yeah. It might be the case that you actually need to make sure that this thing is a list, but if split is by default giving you a list, then it would be redundant, yeah. Yeah, Jonathan?
From a syntax perspective,
I'm not sure. I've only used it a couple of times, but I suspect, yeah. Yeah, Covey?
Maybe a dumb question, but where it calls line num in the next bit, how does it know what that value is, since that value was an index for the previous for loop?
OK, where it calls line num, how does it know? Is your question about what enumerate does, or am I misunderstanding?
No.
Did you say skip rows equals line num?
Yeah.
Your line num came from the for loop from before.
Yeah. Oh. Yeah. 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 It's what, yes, it is what I know it's what we want. My hesitancy was, why is line num now set to that particular value? And yeah, it's because of the break. So Veronica, thank you. So yeah, the point here is that this kind of awkwardness with the break, the random break statement here, is that this is an awkward thing to do, which is why I'm giving it to you, because it's going to be the model for what you're going to do in part 3, and probably none of us in 30 to 45 minutes of working on it would come up with a solution that actually solves this on our own. Yeah?
Can I just say, I believe that you were expected to solve. So,
Yeah. I want you all to have fun with the Titanic problem and not just be frustrated until 3. So, yeah. There's another thing here. A more reasonable option for solving this problem is you go through and delete all the bad stuff, and then you can just read things in. And then the third solution is that this awful format, the kind of data parsing stuff that is provided above, has been built into AstroPy for you. So that's another option, but you should be aware that not every file format you're going to encounter will have some built-in reader. So, okay. So I hope that provided enough to get to now read through part 2 and move on to part 3 and attempt part 3. Don't bang your head against the wall for forever. Part 4 is interesting and a lot of fun, and I think more like problems you'll encounter more regularly. So, yeah. Okay, that's all I had.